Yes, Chandan, you have a question?
Yes, sir. For the previous
Mm-hmm.
inequality, then I'm getting that it is true.
No. Jensen's inequality will no. Don't use. Sorry.
Gibbs's inequality.
Shebishep, no. Don't use that because see, certainly you're applying. You may be applying it in a wrong way because that it's a complicated inequality, right? It has some conditions. Okay, it has some conditions, so you have to be careful when you're using it. There will be some increasing, decreasing condition. You agree, right? In that, so yeah. Usually try to avoid such that those are yeah. And also then you have to prove it. That's not a trivial inequality to prove, I think, for integrals. I mean, I'm not saying it's hard, but okay. So let's get to some more serious stuff. So I so we have done so we are going to look at what are called C infinity functions. Okay, this is a very important concept for several reasons. C infinity functions. So these are basically the definition of this is functions which are infinitely differentiable. Okay, so we are going to look at functions which are infinitely differentiable, which means that what does it mean? It means that for every n, that nth derivative exists at all points. So it's from R to R. Okay, I want to distinguish these functions from, sorry? No, I'm saying, yeah, but I'm saying more than that. Can anybody say the definition of this again? That's right. Okay. So what are examples of infinitely differentiable functions? So we have these, obviously we have the obvious, yes. So we obviously have the obvious examples, but there are some very canonical examples, and that will be something like you would know this, 2x, 3x square, but there will be a small condition here that is x is between 1 and -1, right? This kind of function is infinite. What does this mean? It means that for every x, you are evaluating this series, and that is the value. And it can be evaluated because it converges, it's bounded, and so on. If x is between -1 and 1. You do this for every x between -1 and 1, you get this function. Just the natural thing. Now, this kind of functions are infinitely differentiable, right? These kind of functions are infinitely differentiable. Such functions, I'm just writing just words, not writing sentences. These kind of functions are called power series. Okay. Power series are also a very special topic, which we have not done mostly anything, I think. Okay, these kind of series are called power series. Now, all of us know that power series are definitely a very useful thing, right? Because they help you to understand functions in like you understand polynomials, right? We have seen their usefulness, like when you do your sin x, cos x, when you write the power series, and suddenly you can find all kinds of things about them, right? You can prove all inequalities. Taylor's theorem tries to get a power series when possible, or if it's not possible, then just a Taylor polynomial. And then you have used it in calculating limits. So power series is definitely a very important thing. If for some function you can write it in terms of power series, then it's very good. Okay, so one very central question is when, which we are not answering, okay, when can a function be written as a power series? So from what I have said, and you can just kind of understand, this is certainly a very useful question if you can find conditions, okay, when a function can be written as power series. Now this question has a very precise answer, but we are not going to do that now. That strictly speaking lies in what is called complex analysis. Okay. But for us, we see that power series is certainly examples of functions which are infinitely differentiable. And we can even say what the nth derivative is, right? You can write the nth derivative in terms of the coefficients. You can just take the derivative in times and you can derive a formula. So, an by n factorial at 0, whatever. And a derivative at 0, so on. But here the question is, are there C infinity functions which don't have a power series? Okay, so here is your class of C infinity functions. It's a big class. And here is your class of functions which have power series. These have names, they're called analytic functions, but power. But we just need to see them as problems for now. Power series. Are there some things which are not, which are kind of on the boundary?
By using Taylor's theorem, we can
See, yeah. So what do others have to say about this? That's a good point. We all think like this. When I used to think like this in high school. So he's saying that using Taylor's theorem, which I think all of you at least roughly know, right? So Taylor's theorem, I'm not writing this. Using Taylor's theorem, we can write every function in terms of power series. So why is that not correct? Or is it correct that then every function has a power series? So he's saying that you can start with a function, f, fx, and you can write its Taylor series expansion. No, but let's assume that it is infinitely differentiable. Then where is the problem? Can anybody? This is a conceptual question. Can anybody point that out? There is still a problem, and that is basically what we are kind of investigating. See, if the function is infinitely differentiable, then I can make this Taylor series, right? But no, it is defined, it exists. All the derivatives exist. F is a C infinity function. Okay. Yes, right? That is the thing. Does everybody agree with that, right? I mean, the series can still diverge. There's no guarantee. See, this thing, when you expand it at many finite points, you will see that at x equal to 0, they'll obviously will match because that's how you have made them. The derivative at x equal to 0 will match. The derivative at the second derivative at x equal to 0 will match, and so on. But that does not imply that this function will be equal to this, right? And more than that, it doesn't even imply that this quantity is going to converge. I mean, it could just go to infinity. For any x, it may happen that for every x, it goes to infinity except for s equal to 0. So you can associate Taylor expansion, but the Taylor expansion need not be equal to the function at each x.
But actually, I haven't really understood.
No, but see, you don't know. We are not proving anything. See, there is this function f, and there is this other series that we are associating with it. Right. We usually misuse the language. We say that Taylor expansion of fx. But just because someone says that it is Taylor expansion of the function, it doesn't mean it has to be equal to the function.
Yes, sir. Like it's the best possible polynomial which approximates.
Yes, you could say that. Yeah, it is the, well, yeah, okay. It's not the best. It is the best possible. It's a little more than that. It is a polynomial which, let's say, if you do it till n terms, then it is a polynomial which approximates fx better than x to the power n, like the difference, the error, goes to 0 faster than x to the power n goes to 0, so on. But yeah, it's loosely speaking, it is the best approximation up to n. But then that doesn't mean that when you take this to infinity, that this will be equal. There's no guarantee. Like the best approximation itself may not be good enough, right? That may happen.
Sir, in the end,
Yes. If we expand up to n, then it is the best approximation, right? But that does not imply that it has to be equal to fx. I mean, even when you take it infinite many times. Certainly, so basically there's no reason why this should be equal to this, right? I mean, we expect it, but then there can be counterexamples. And the main thing is that it may not even converge. But here is the thing. Let me change this series. Let me make it a general series. If px is a power series, and let's say px, we expand it like a1x, a2x square, and a3x cube, and so on. So it just goes on. Okay. Then we know that px kind of behaves like, so px to some extent behaves like a polynomial, right? Px behaves, you could say, a bit like polynomials. So in what sense? In sense that, well, when x goes to infinity, we can surely say that px, so can we say, so when x goes to infinity, can we say that px goes to infinity or minus infinity? This is a question. Can we say this? That when x grows, px should also grow? Okay, like the terms could be negative also. So you're saying it may not be true, right? Okay. Okay, let's see. Anyone else?
so if you take the example of 1 minus x to the power of minus m, then for x tends to infinity, px.
Right. So 1 minus x whole to the power n, as x tends to infinity, px tends to 0, and this certainly has an expansion, right? So it certainly need not go to, so this is not correct, right? This is not correct. But what we can say is px is determined by the derivatives at 0, right? So px is determined by p of 0, p of 0, p dash 0, p double dash 0, and so on. right? This thing we know. Do we agree, right? Because you can find these coefficients in terms of these derivatives. Right? You can find these coefficients in terms of these derivatives, right? So Px will be well behaved in the sense that, I mean, if all of these derivatives are zero, then it has nothing to do. And P of zero is also, then there's nothing to do. But otherwise, if at least one of them is non-zero, then Px will also be non-zero. Px cannot become zero, right? As you keep changing the x, right? So the question is, does there exist an interval a comma b such that p of a comma b, p is zero on a comma b, and px itself is not zero? So this is my question. Let's think about this. So here the thing is that this x is from infinity to minus infinity. So these questions are meant to just tell you the sense of how these things can behave. Okay. So let's see. So is it possible that a power series is zero on an interval, but then non-zero outside? So there is an interval on which it is zero, but then it is not zero outside that interval.
Sir, that is only possible if all the differentials go to zero.
Right. Okay. Then all the differentials at what point? Yeah, it's better to be safe. You should say between A and B, right? So that implies that for all C in between A and B, P, the nth derivative at C is zero. That is just simple to see, right? But this implies that you can just try to expand this thing in at C, meaning that you can write this Px around C. So you can say, I will write it like this, and then you can find the coefficients. And when you find the coefficients, you will see that they will be these things by taking derivatives. Okay. Obviously, we are using a bit of analysis. We are skipping a bit of rigor here, but you will see that then these coefficients become zero. And then, but once these coefficients become zero, so that will imply that each pk is zero for all k, but that will imply that px itself is completely zero. Okay, so I mean, like polynomials, when they vanish on finitely on like an n degree polynomial, when it vanishes at more than n points and it becomes zero. In this case, it is not so good. I mean, power series can vanish at infinitely many points, but if it vanishes at an interval, even if it's very small, doesn't matter, at a continuous interval, then that implies that it is just zero everywhere. These small properties, this will turn out to be very useful. Yes?
We see its geometry
Yeah. Geometry. Yes. So the problem is that the geometry of a power series is not, so to see the real line is not the right place to see the geometry of the power series. The right place to see is the complex plane, but then we have to say some things more. Okay, that's why I said the study of this really lies in complex analysis. But obviously this is a topic in real analysis also, but the geometry is not that visible in real analysis. Okay. Yeah. So, right. It is made up of these things and right. So then I think once again, this is good. Okay. Now we can say more things, but we want to now do a concrete problem. So let me just get to the problem. Maybe so we have seen that a power series, if it kind of vanishes at a small interval, it vanishes everywhere. Now we want to say that there are infinitely differentiable functions which do not have power series expansion. Right. And the way we will say is this: make a C infinity function which is infinitely differentiable. And this will be a very conceptual problem, and means it will involve both concepts and solving. Make a C infinity function which, so you will just see, which is non-zero, or rather, which is 0 on the interval a comma b. Okay. And so, this is, if you want to make a function which is C infinity but not power series, this is what you will try, right? Which is 0 on an interval and non-zero, like never 0, you could say, or you can make any, but just non-zero on minus infinity to a, maybe a, or maybe we can just make this closed even. Well, it will be closed because of the limits. Yeah, a and union. So first, what is the reason behind this problem, right? We have seen that a power series, when it vanishes on an interval, then it vanishes everywhere. So if you want to make a function which does not have power series, or which cannot be written as power series, then this is what you should aim for, right? Make something that is 0 on an interval and non-zero outside. Okay. The idea of power series is that it is determined by, or the derivatives at one point. So yeah. So basically, one thing about, I'll just say this before we think about the problem. This is what I can just slightly extrapolate, or rather restrict to the real case and try to say about the geometry. It's not much the geometry. There is a little bit of a physical tension here, physical thing about power series, that so it's no more static geometry. So when you see this power series like this, the next thing you can write it like this. Now, if you just stare at this, it's actually a pretty fantastic thing, in the sense that just knowing, you would think that just knowing the values at one point, it is telling me the values at every point. In just this thing, this fact, right? That knowing the derivative and value and the derivatives at one point, just the local information at that point, that has a global information. All these derivatives are local information, right? You can calculate them in a small interval. So maybe whatever, doesn't matter. Right. So let's just, so we'll come to that. That is probably the right example. But if we try to understand this thing, so this is like some sort of an intuition, maybe, that just the values at one point are telling you the values at every point, right? So this is kind of saying that this graph that you're looking at, or maybe just this line, this red thing that you're looking at, right? It is not like a static thing. Okay, it is not like a solid static thing. You can kind of say that there is a very thin, some tube or something, very thin tube, and there is fluid flowing inside it. Okay, there is just fluid, it's just filled with fluid, right? Then, so basically there is a global interaction. Okay, whatever happens, like small movement here at the origin maybe, will create a movement everywhere. So there is a pressure, there is this, you can say it formally, right? So there is a fluid and that kind of, creates this tension everywhere. So a movement at one point, or whatever happens at one point propagates everywhere. Okay. And this is a precise thing. This is a precise thing. What happens in the complex situation is that from C to C, when you have such a function, then if you, let's say not from C to, but let's say from an open set of C to C, if you have a function, then this kind of function, which has this kind of expression, then knowing the values of the function on the boundary will tell you the values inside also. Will tell you the values everywhere. Those functions have this property. Like here, knowing it at a point is telling you the value everywhere. There, knowing it on the boundary will tell you everywhere. And that's again modeling the same thing, right? That there is some sort of a global tension, push and pull. So what happens at the boundary kind of determines what happens everywhere. And these are precisely the things that these complex functions try to model. Okay, like wind flow, current, this pressure, this heat equations are there and things like that. So this is more about what they are modeling, the physical things. Okay, but then even though they are modeling physical things, it's the same language of derivatives, the same just extension of the language of derivatives, just the same language which we use now. It just works out there also. So that's a fantastic thing. But anyways, so that's the intuition. Okay, so now coming back. Yes, so Raghav, you were giving us an example. So this is an example of what? Okay, when x is not equal to 0 and 0 when x is equal to 0. So what? So such a function. So, but it is not 0 on a comma b. Why? No. On it should be so. So your answer is probably correct, but it is not the answer to this exact question. In the sense that, but it's not. I think that's not trivial to prove also. But let's leave that. Point is, what I'm asking is that it should be 0 on this interval, but this is not 0 on this interval. On any like this function is not 0 on an interval. Okay. Okay. But obviously it's a fact that, but I'm not asking it because I don't think you guys can prove it if you don't know that this does not have a power series expansion. You can try to prove it. I'm not going to that because that is not the purpose. Okay. Yeah, so you can prove that this is infinitely differentiable, but not doesn't have a power series at 0. But that is not the way we are going now. So let's look at this problem. So forget about power series now. I mean, you don't really need power series to do this problem. Okay. So we kind of want a function which is maybe a here and b here, and it is 0 on this, but suddenly it jumps. But then we want a smooth function. Okay, we don't want these sharp edges. So what do we do? Okay, think. Converges to that. Hmm? You mean something like this?
No, initially we had those
Straight lines, right? Yes.
So with a straight line, let's say that's slope n.
You can just take slope 1, yeah. Or
We can say that we need which after d behaves like whose slope behaves something like, for example, 1 minus e to the
1 minus e to the minus x, whose slope, oh yeah, you're right, whose slope is like that, right? So you're saying that, so this slope is becoming 45 suddenly. That is the problem, right? Everybody sees, I mean, not the slope is becoming 1 suddenly. That is the problem. So we want to make the slope 0 there. But how do we do that? Yeah, so you can say, yeah, it's somewhat like this, but yeah, how do we formalize that?
it has to be a single analysis.
See, it can certainly be piecewise. Single expression doesn't also mean analytic. Analytic is something different. That means it has a power series, which this function will not. Yeah, it can have a single, but it should be infinitely differentiable. That is the condition. So maybe, so these straight lines can be misleading. Okay, so don't like focus too much on that. You can think freely. Okay, so please think freely, because this on maybe the straight lines can actually be like, it's useless. Okay. So the function should have a skeleton which allows it to change its values, but then they have to put the flesh in the right way so that it is differentiable. The problem will only be at A and B, the differentiability question, right?
Or should we use that limit with the differentiation, this one, limit f of x plus h minus f of x by h
Uh, limit, yeah, so you would need that because you want to check the derivatives at a point, let's say A and B. But first, maybe you have to know the idea, right, about how this is going, how this is going to go.
is it 0 or not?
At A and B, it is 0. It's on the closed interval. On the closed. Yes. Sampad, you were saying something. E to the minus x minus. Am I writing it correctly? E to the minus. Yeah. E to the
x minus b may be the x is factored and it's not in the bracket like x minus b e to the so v is the e is multiplied with b.
okay. 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 But this won't be 0 on a comma b on the entire interval. It will be 0 on b. Yeah, sure. I think we can do if yeah. Okay. For x bigger than b or bigger than equal to b, doesn't matter. X bigger than b. Okay. And surely 0 on a comma b. So just right now we have the opportunity to check if this is correct or not. Right. So just with this itself, we can try to figure out what is f dash b. Or does it exist and what is it? Right. So let's see. So let's if you take the limit, let's do it the usual way. Let's take the positive limit, then f of b plus h minus f of b. So f is this function, right? This is f by h. And then, so what will it be? So f of b is certainly 0. That's written. F of b plus h is b plus h, b, b, h by h. Am I doing it correctly? So, am I doing something wrong? B plus h. Yes, because in place of x, you just replace by b plus h. Right. Right. And so now if we take, but then it's b plus h minus b e to the minus h. This limit is a little strange, right? It does not exist. So just see, it is a little different. Yeah, this x that is present separately, this is not, yeah, it's a little strange. That is what is creating a problem. So it's like we are taking, yes.
If we just take, so if we just differentiate b minus x, both x and I mean both of these individual terms are differentiable.
At right, and at b, that expression itself doesn't make sense.
freeze with the value at the previous piece, because it can we just take the derivative at only the point that still works?
No, because yeah, can anybody say why it doesn't work? Yes, that's the simplest reason, right? That's Mhm.
For discrete values, if we can for construction of that Lagrange interpolation,
Uh-huh. Uh-huh.
where at certain points the function vanishes.
Mm-hmm.
So can we like modify that kind of function
No, I don't think so. Because an interval has uncountably many points, right? And even if you, yeah, if you understand, right? So it will not work, I think. Yeah. Haha. Yeah.
I do not understand. So if we have a piecewise function,
Mm-hmm. Yeah.
if the if the one of the pieces is differentiable everywhere,
Uh-huh. Okay.
and at the point where you break the function into pieces,
Mm-hmm. Mm-hmm.
uh, if the if it is continuous at the
At that breaking point.
so yeah, shouldn't the right derivative be shouldn't that exist?
No, the right derivative exists, but that is not enough, right? If the right derivative exists, then
The right derivative is exactly the same as the derivative of the right hand side because it was differentiable also. So there's no new expression there. So let's write, like, for example, f of x equals
f1x,
yeah, in the interval maybe to a
right? A closed. And so what is the function in this piece?
f1x, or we can call it x of b.
Yeah, f1x.
No, not like that. I mean,
Oh, yeah, yeah. Okay, okay, sorry.
yeah, and after a, it's
Mm-hmm.
if f2 is differentiable at all points, just
Mm-hmm.
in frequency, and let's say the value of f. So this function f(x) is continuous at a.
Mm-hmm. Mm-hmm.
Shouldn't the right derivative of f(x) be just the derivative of
f2x. Yes, yes. So the right there, okay, so I saw, yeah, that's what I was thinking you were saying, right? So the right, so you're saying that the right derivative should have existed.
yeah, and we were trying to just find the right derivative. Shouldn't the absolute derivative of x be equal to a?
Yes, yes, yeah. So that's what you were saying, yeah. Yeah, so why is it not existing? So something we are doing is wrong. So let's see. It should definitely exist. So maybe that means that calculation.
Derivative of x minus y.
That's right. That's right. But then from the calculations, it's why is it not coming? So and b it is 0. Yeah, that's right. Some calculation is wrong, right? That's the thing. That's correct. So then, yeah. So yeah, the derivative should uh, exist, and it will exist, and it will be 0. So both should exist. But I just want to verify it through the calculation also. Means where is it wrong? So b plus h minus b. Did I not put this? Put this b. Yeah. So that was a simple point which I was missing. So x by h. I still can't see the mistake. Oh, no, that's because this limit exists. This limit exists. Sorry, right? This limit obviously exists. Or Yeah, is this right? And then this is what? This is 1, right? Yeah, -1. But then again, I'm getting something else. Yeah, but never mind. But this limit does exist.
Yeah, it is 1 minus b. So even if we differentiate the
Yeah. Okay, so the right derivative is 1 minus b. Yeah, 1 minus b. But yeah, but that's right. But this is no, this is 1 minus b because that's what we're getting. Or no, there is a minus h, right? That's why you're saying. Yeah. Yeah. Okay. Right. But the problem is that then, so this is the right derivative, but the left derivative will, maybe I can put a plus here, but the left derivative will not be the same. This is going to be 0. This is going to be 0 because the function is 0. And so that's where we are in a problem. But yeah, the point was correct. Obviously, right derivative should have existed. So we need to make a function which is whose derivative at b is 0. Okay, so remember that the goal should be that f dash b, the derivative at b should be 0. You can forget about a for the time being.
So then maybe constructing a piecewise function so that after b, which our right-hand derivative will also be 0 and at b.
Yeah, that, but so I mean, we can just we can give an example of such a function, right? Quickly. Can anybody? I'm just erasing this thing. It's not difficult. But whether it will become infinitely differentiable, that's a question for later. But at least first conditions we can meet, right?
We can just add to this function b into
So,
I think so. Like
uh-huh.
working for e function because like go to much basic function like sine and cosine.
Yeah, sine and cosine. No. You have to see that. Okay, so let's for example, let's take an example of like sine. So you can say something like cos of, so what is the example?
Sine of x minus.
Yeah, okay. Sine of x minus b. So we will see, we will see where is the problem with this kind of example. Okay. So let's see. Why E is much more favorable, we will understand through this. Okay. So let's say that f is, so sine of b what, b minus x or x minus b? X minus b. Sine of x minus b for x bigger than equal to b, and otherwise it is 0. So certainly we can say that f dash b is 0. So f dash b exists and it is 0. But where is the problem? Can anybody point? So this will not work, but we should see why it does not work. Then only we can say, right? No, why? Oh, no, yeah, right. So you have to take something else, something, I mean, yeah, I don't know. You have to take, so what should you take? Something like this. We can take 1 minus cos, right? 1 minus cos or just, yeah, right. Yeah, just flip it and so on, right? So 1 minus cos, yeah, that's what I was, right, correct. Trying to think. So 1 minus this. So this one certainly works, yeah. So now for this function, it works. But then where is the problem with this kind of example? So obviously this, so on. I mean, so obviously it's non-zero. So the non-zeroness is not the problem. The higher differentiability at B is a problem. Okay? So this is not smooth enough. This is not smooth enough. Obviously, I'm just saying it. How do you prove it? I mean, I've not proved it, right? So we can go to the second derivative. Okay. So so first derivative we know exists, but the second derivative, we can try to see. So the second derivative at B. So for this, when you do, you will see that there is a, so you take the second derivative. So you take the first derivative at B plus H. And this is the problem. Okay? Because the first derivative at B is 0. So it is like one of those sine 1 by x, that it is continuous but not continuously differentiable, it is a bit like that. Okay. Yes, that's better. Actually, that's better because when you take the normal derivative, yes, yeah. Basically, I am doing more or less the same thing, but that is faster, right? I mean, you can do it both ways. So just take the normal derivative and you will get, so what will you get? Cos is minus sine something, right? Something you will get like this. Yeah. And then this by h goes to, so what will this become? B plus h. Hold on, something is wrong. So this is the x, so the x will become B plus h. So does it work? Or does it work? Seems to work, right? Yeah, so this is also 0. So yeah, the left-hand derivative will certainly be 0. Oh yeah. So okay, sorry, yeah. So this does not work. Yeah, this is 1. Yes. So you can adjust it. So it doesn't work, right? Because it's the right-hand derivative is 1 and the left derivative is 0. Oh no, because sine h by h, that's 1, right? No, but the b cancels. But the b gets cancelled. Yes. Yeah. So this does not work. Okay. This does not work. So I'm just giving it a homework, okay? Because today this class was just almost like a burst of class. Started very late and so not very good today maybe. So I mean, we can do this now, but it's better that you guys think about it. Okay. So I mean, not this, but this problem. Okay. Please think about this problem. Okay? So the main thing is that if you try to attach, if you try to take something here and just try to maybe artificially try to attach, you have to take something like E, because it should, like, when the derivative of E is 0, then the higher derivatives and all, those should also be 0. Okay, so E is better there. In the sense, the way I was saying is not in the attaching sense, but my idea was that you take the skeleton, which is maybe you take something like this. Okay, you take something like this, and then you can write this function. Then you multiply this with some function which is like a e to the power something. Okay, and that is powerful enough to tame. So that at that point it will smoothen it. If you take some other function which is like comparable with x, because this is like a linear function, then that will not be able to tame it. Okay, so you need a more powerful function like e. So you will need, so the idea is, for my idea was to first you take this kind of function, this. So you take this equation of this line and this line, and with that you multiply with a suitable function in E so that the derivative at B is 0. And you can easily make such an example. Okay, and yeah, then you have to show for the higher derivatives. So please think about this. Okay, so usually we'll start much earlier and do the class properly. So yeah, so that's it for today. Yes, any question? Yes. Oh yes, this one. Okay.
And the problem was that the derivative was on the left side we get mark 0, right?
Mm-hmm. Right.
You can try to fix that by adding a term
Adding x minus b.
and equal into so that at b is 0 still, right? The extra term is not added anything.
Right.
And the derivative is either 1 plus b or 1 minus b, one of them, whatever the derivative of the left term is,
Mm-hmm.
so that it cancels out that effect.
Yes, but that will not work for like when you go to higher derivatives. I get a feeling that it will not be good enough. Right? Please check it. Okay, because it seems like, yes, and I feel that this will not work because this seems like we are taking this function and we are kind of over it. We are putting this function, and they're taking the effect of that. That I don't think is good enough. Yeah.
The second derivative
Will,
is the other one is
yes, so that kind of problem. So you have to get you'll get the intuition, but when you multiply, then it has a different sort of an effect. So that is, yeah, please think. Okay, next time we will say this more properly. And yes.
So can you take one class on install C0
Actually, I had prepared. I wanted to take it,